Our next speaker is going to be Joe Huba. And with any luck at all, we'll get that going quickly. Joe is going to talk about gravity wave seeding of equatorial spread F. Thanks, Joe.
Thank you, Dave. Okay, so some recent work we've been doing over the last 6 to 12 months with Dave and Dave Heisel and others. So equatorial spread F, when I give this talk, it's always to people that know about equatorial spread F, but there's a lot of gravity wave people here that maybe don't know about it, and I failed to give a good tutorial. But be that as it may, equatorial spread F is a post-sunset phenomenon, usually in the equatorial ionosphere, where the ionosphere becomes horribly unstable. The bottom side of the ionosphere has a gradient opposite to gravity, so it's like a Rayleigh-Taylor instability that just blows up, and you get giant plumes of electron density bubbles just rising up, sometimes over 1,000 kilometers, and it disrupts communications and GPS and the like. It's variable on a day-to-day basis, and that's sort of one of the mysteries, and of course there's lots of factors that might cause that, but what we're investigating is gravity waves as a seeding mechanism to this instability. You know, if they're there, maybe we can trigger them. If they're not there, maybe the instability is not triggered. So that's the motivation. As far as, you know, how do gravity waves actually affect the ionosphere in such a way to drive an instability, these are the equations, or the velocity equation we're solving. And the gravity wave we're introducing as a perturbation to the neutral wind. So we're modifying the zonal and vertical and meridional wind with the gravity wave. And that wind can come in two places. One is right here, and this is just a direct coupling along the magnetic field line, collisional coupling. So you can have a wind enhancing the gravity wave, pushing electrons up or ions up the field line or down, depending on the direction of the wind. And I think that's what Sharon was talking about in the previous view graph. The other way is through the electric field. And in the ionosphere, the neutral wind in the low latitude region basically drives a large electric field that transports the plasma upwards during the day and downwards during the night in general. So by perturbing the neutral wind, you can perturb this electric field. And then this electric field can disturb the plasma all along a field line. So it's not just localized where the wind is, but it leads to a global effect along a whole field line from one hemisphere to the other. And so what we've done is two studies. Our early studies, we just took some analytical expression for gravity wave winds just to see, you know, what's going on. And then we got some recent data from Dave Fritz. It's very preliminary, but it's a data set with some interesting gravity wave features that are more realistic than a simple analytical expression. So the first thing we did was use this simple, relatively simple dispersion relation for the gravity waves. And we varied the intrinsic gravity wave period, which modified m, which is the vertical wavelength. So we did a number of cases, 4 cases in particular, where we did different periods and wavelengths vertically. And then we have a formula, basically a sinusoidal formula, to modulate the zonal neutral wind and the vertical neutral wind. So these are the modifications from the gravity waves going into the code. These are just some numbers. The high key point I want to make is I'm going to be contrasting case 1 and case 4. Case 1, it's a relatively long period of 60 minutes, and it has a relatively short vertical wavelength of 43 kilometers. Case 4, it's a 15-minute period, but the vertical wavelength is close to 300 kilometers, and they're the two extremes. So in terms of perturbing the system, where do we perturb it? This is a contour plot of the electron density in latitude and altitude. These are field lines, the white lines, and then you can see the contours or color contours of the electron density. And this is the sort of equatorial anomaly where we get these two crests off from the magnetic equator. So when we're looking at perturbing this system, we usually perturb it here on the bottom side of the F layer at the equator. So this is where we sort of naturally would put in perturbations. In this particular case, we're restricting the gravity waves to lower altitudes, and we're putting them off from the magnetic equator here. And the idea is that you're perturbing the system here, and because of this effect on the electric field, it maps up into this region to perturb this region, and that can drive the instability. And I'll just contrast these two cases here. These are, again, color contours of the electron density. The x-axis is longitude. This is the east-west axis, and this is probably about 1,600 kilometers spatially. It's 16 degrees. And we're going from about 100 kilometers to 1,000. And this is the F peak. The maximum electron density is about here. So in case one, this is the short vertical wavelength case. This is about 2 hours after we have initiated. You can see that there are some perturbations on the bottom side, but not much has happened. By contrast, this is case 4. This is the case with the large, almost 300 kilometer vertical wavelength. And you see these large bubbles rising, which are characteristic of equatorial spread F. So there's a distinct impact on the type of gravity wave that you impose on the system in this model to whether or not you can actually trigger bubbles or not. And we're, okay. So we're also working with Dave Hines, who has a completely different model to study the same phenomenon. And the big difference between Dave's model and our model at NRL is the electrodynamics. And in our model, we assume that the field lines are equipotentials. It's a 2D problem. So along the field line, the potential doesn't change. Dave and co-workers at Cornell have modified that to allow potentials to change along the magnetic field line. So he has a three-dimensional electrodynamic solver. So that's the major difference. And this, again, is a simulation of the impact of the gravity wave on the ionosphere. And of course, again, you can see bubbles forming. There's different numerics and other things going on, so his bubbles look quite a bit different than our bubbles. But the important point is they do see bubbles. So the actual details are something we're working on to try to understand the differences, but in two completely separate codes, we are triggering these bubbles with these gravity waves. In our situation, what I'm plotting here is the maximum upward velocity on the grid as a function of time. So when these bubbles form, they're propagating upwards, and they're going upwards because of an E cross B drift. So you sort of like a capacitor-like thing. You have an electric field, there's a magnetic field, and you drive the plasma up. And as the instability progresses, this field gets stronger and stronger, so the vertical drift gets larger and larger. And we use that as a proxy to measure the growth rate of the instability. So these were the four cases, the short vertical wavelength and the very long wavelength. And you can see here these oscillations. That's from the gravity wave with a 15-minute perturbation. Down here is only about one. It's a 1-hour perturbation. And what's interesting is, first off, at this point in time, a little bit over an hour, they all take off. And if you look at the slopes here, they're all about the same. So you perturb the system, it goes unstable about the same time with the same growth rate. But in case one, we didn't see any bubbles. And it's because the initial condition, the initial perturbation was so small. So this particular perturbation from the gravity wave only generated about a 10-centimeter perturbation in the velocity initially. This case 4, it generated a perturbation of a couple of meters a second in the velocity. So it's sort of like this guy has a big head start, and so bubbles can form. Okay, so the next thing we did was we're trying to ingest gravity wave data, similar to what you'd seen earlier from Dave and Brian. And the first data set was basically a box of 120 kilometers by 120 kilometers, 120 kilometers. So it's relatively small. So you can see how small it is relative to the ionosphere in terms of latitude and extent. This is longitude. We've now shrunk it down to about 1 degree. And then this is the vertical extent, although the color should fill the whole thing here. And when we use that as an initialization in our code, I won't go through the details, but once again, we generate these bubbles that are forming. So again, whether it's a relatively simplistic analytical expression for the wave or real gravity wave data, or closer to real gravity wave data, we are triggering the instability. Again, Dave Hines also looked at it, and you can start to see some also perturbations here and growth of the bubbles in his model. So one difference here is the data set we had was for about 1 hour. So we ran it for 1 hour and then let it just keep going, where we just turned off the perturbation. So this is about 2 hours after the initialization, so we get these large bubbles. In Dave's case, he just ran it for about 1 hour and stopped. So he didn't give it time to actually keep going. So again, the results are reasonably consistent between the two models. So now the latest stuff we've been looking at is the following. We've been confining the perturbations in latitude to about, say, 10, 11 degrees. But what if gravity waves extend in latitude everywhere? So you have the possibility that, well, we can put the same wave spread over 20 degrees here or so. In that case, the perturbations on both ends of the field line would be in phase, and you would expect it to enhance the instability. And what if you took another case where you put them out of phase? So in the northern hemisphere, we have a set of wave perturbations, but in the southern hemisphere, we just reverse everything. So now they're out of phase. So you have the two hemispheres kind of fighting one another. And what does that do to the instability? Well, the top case is when they're in phase. And again, this is about 2 hours after the run, and you can see bubbles forming when they're in phase. The bottom panel is when they're out of phase. Again, you can see perturbations on the bottom and things are starting to form, but you don't see large bubbles forming. So you have a situation where gravity waves can trigger the instability, and depending on phasing and locations and amplitudes, they can actually do nothing, cancel everything out. So this is a quick summary. The bottom line is, one thing we learned from this is when we were sort of thinking about having gravity waves trigger spread F, we were always perturbing the system over the equator at 300-400 kilometers. And so we thought, oh my God, we got to get gravity waves up that high. Hey, that's hard to do, maybe they're useless. But what we're finding is all we have to do is perturb the system between 100 and 200 kilometers off angle. We perturb the electrodynamics of the whole system, and then that can trigger equatorial spread F. So that's one, I think, important thing we found so far. Now it's a matter of, using better data from gravity wave simulations, more realistic, and tie things together. But I think it's a really quite a good start and quite interesting. Thank you.
Thanks a lot, Joe. Any questions? Erdal.
Yeah.
Thank you for the interesting talk. I think this gravity wave coupling into the ionosphere is very interesting. I was wondering, are you propagating gravity waves through your system, or are you imposing those perturbations in time, constant perturbations in time, around the equator? Because that region, 100 to 200 kilometers, it's a very dynamic region in terms of gravity wave effects. So gravity waves continuously propagate into the thermosphere at those altitudes, and they change the circulation, which affects the gravity wave propagation. So if you continuously perturb your system at your lower boundary, I think it's 100 kilometers for some.
Between 100 and 200.
Yeah. So I'm not sure how realistically this effect is captured, that coupling effect. Waves coming below, changing the circulation, and how could you assume the same amount of perturbation for a certain period of time?
Okay, let's see. To start, we start simple. We just wanted to see if something would happen. So you take the simplest sinusoidal wave. Do we get something? Yes. All right, sort of interesting. Now we're trying to use real data from the simulations Dave's providing that encompasses, incorporates some of the effects you're talking about. So the perturbations, yeah, they're generated, and we keep them going in time and varying a bit. But in reality, from that one figure I showed earlier, if I can find it. Yeah, this one. So actually, you only have to perturb the system for a little while, tens of minutes, maybe 30 minutes. And once that gets triggered, you can lead to an instability. So, I mean, your point's well taken. And, you know, it's the directions we're trying to go to figure this out.
Erdal, I can comment on it as well. The numerical simulation that we provided so far was intended to reflect local forcing, as Joe says, for a short time, following the change in the tidal wind from westward to eastward, which is the condition that we know needs to be in place for ESF seeding. And so the perturbation assumed that an eastward tidal wind for this local environment, short time, and a westward propagating gravity wave in that. So it's consistent with the larger scale dynamics that we expect.
I have a quick question.
Sharon?
Oh, sorry. I have a quick question. The last slide mentioned there's a relationship that needs to be the phase of the gravity wave in order to trigger ESF. And I'm just wondering if you can just describe, using your hands or something, just the geometry of what's going on, like the orientation of the magnetic field line and the orientation of the gravity wave. Do they have to match exactly? And how does that kind of look?
It's hard to see here. I'm sorry.
Yeah, so I was wondering if you could just use your hands and just describe what you're doing, what's going on.
Yeah, I know. The idea here was, you can't see it, but right here there's a red and then a blue. And that's sort of the vertical velocity of the plasma being driven by this perturbation. On the other hemisphere, it's sort of like red-blue. They're out of phase on the two sides. So here we're trying to push the plasma up. Here in this phase, we're trying to push it down. And you do basically an integration along this direction, and they cancel. So what the dominant component is of the neutral perturbation, whether it be U prime or V prime or W prime, that's what we're kind of looking at to see what's the most important effect in here. But the bottom line is, when you do these instability simulations, you're doing integrations along a field line. And the perturbations here and perturbations here can cancel, add, whatever. And that's what I mean by the phasing. Yeah.
One more question, Greg.
From an observational standpoint, what would you need the empirical community to measure? Given that we only see air glow over a limited range of altitudes, what kind of sensitivity and what kind of measurements would you need to see to corroborate what you're pointing to here? Have you thought about that?
Not really, since I just do models. Yeah, that's really hard. I mean, the whole problem of spread F is pretty hard. So if somehow you could find 2 days in a row, one day with spread F, one day without spread F, and kind of sort out what the differences are, and then maybe look for some data in airglow of something that would trigger this. I don't know. Actually, I have no idea how you would assess some of these perturbations.
Based on the way that you stimulate it, though, what amplitude, what size of a modulation would we need to see at about 120 kilometers that would make the difference between yes or no?
Right. Okay, I guess, okay. The only other thing I can think in terms of a measurement is when you start perturbing a system here, if you have some GPS measurements, you can see, maybe fractions of a TEC depending on the wave behavior here, because they, certainly TIDs get measured with TEC or GPS, so GPS might play a role here for the TEC measurements, albeit weak ones, yeah.
There are opportunities for correlative data sets that might address your question. You can imagine that you could use Arecibo, as Sharon described, and look at convectively generated waves that were excited to the north and propagating southward that might provide the sort of seeding that Joe is talking about, and then use 6300 or the Sao Luis or Hicamarca VHFs to look for responses in the ionosphere.